The next talk is called Apple's iPhone 15 Under the Sea, and it will be presented by Stack Smashing, which is a rather well-known YouTuber with his account on YouTube about security, reverse engineering, and hardware hacking. And we will learn from Thomas Roth about the differences between the previous iPhone generations and the new iPhone generation, especially what's changed with USB-C on the pursuit of root access. So, take it away for Thomas Roth.
Yeah, hey, welcome to my talk. Probably the worst pun on the Fahrplan today. I will talk about the iPhone 15 and the USB-C port on the iPhone 15 and what we can do in terms of hardware hacking on it. So first off, about myself, my name is Thomas Roth. I'm probably better known nowadays under my pseudonym Stack Smashing. I'm a security researcher and hardware hacker. I run a small YouTube channel called Stack Smashing, and you can find me on Twitter at Ghidra Ninja. I also, together with Live Overflow, have a small training platform called hackstreet.io, so if you're interested in that kind of stuff. Now, before we start, there are, with each talk, and each talk about the iPhone, this list gets longer, but basically there are always a lot of people whose work this is based on, whose work I took into account, who I talked to, who helped me out, and so on. And so I want to start by just saying thank you to people such as Carlo Maragno, who was my partner in crime on the Lightning stuff, Jiska, who helped me a lot with, who actually was the initial motivation for all of this too, Caro, Fabian, Lino Sense, Lily, John, Lambda Concept, all these folks did really amazing work. And on the USB-C side, I want to thank Sigusa, T8012 dev team, Mark Zinje, Ollie of Thunderbolt Patcher, and also the whole Asahi Linux team. Without a lot of this stuff would not have been possible. Now, before we start, a couple of clarifications. I will not talk about jailbreaking today. This is not a jailbreak. This is not, a part of a jailbreak. No jailbreaking today. There will also be no exploits or no vulnerabilities. At least that was my initial plan. Until during, doing all this, I accidentally found a couple of vulnerabilities. And so while I can't drop those today, they will be out hopefully somewhat soon, depending on triage and so on. What this talk will be about, however, is hardware exploration. So we will take a look at the hardware on the iPhone 15, how it works, how it compares with the past of the iPhone, and so on and so forth. Now, if you go back over 10 years, this is how iPhone and iPhone connectivity looked. You had this 30-pin dock connector, which was awful. And we will not mention it today, because that will be retro computing already. But after after the dock connector came Lightning, a proprietary connector by Apple that had the awesome feature of being reversible, much more compact, and also less prone to just randomly breaking. Now, Lightning is your typical phone connector, right? And so it can do USB, audio, video, and obviously you can charge your phone with it. But those are not the interesting use cases of Lightning for me as a hardware hacker. So if you go on AliExpress and other pages, you can find different cables for the iPhone. So for example, the DCSD cable, which will actually give you a serial port on the iPhone. And so if you plug this in, you can see the serial boot lock on certain devices, which is not particularly useful under normal circumstances, but it's still pretty interesting. And then another very interesting cable is the so-called Kanzi Cable. This cable is an Apple internal cable that they use for debugging the iPhone. And so it gives you access to JTAG and SWD on pre-production, so engineering or development iPhones. And this one is pretty interesting, and they sometimes pop up on like the gray to black market, I guess. But they are not easily accessible. Luckily for us, a company called Lambda Concept built their own Kanzi cable. And so they used an FPGA, I think, and an STM32, and they built a custom cable they call the Bonobo Cable, which allows you to do JTAG and SWD on certain devices. Now, I was talking about all of this with Jiska Klaassen, and she mentioned that the issue is that basically she can't buy a Kanzi cable because the university will not reimburse her for, a black market invoice. And she can't buy the Bonobo cable because it was out of stock for quite a while at that point in time. Now, I'm a hardware hacker, and so my credo was, obviously, we will just build our own. And so at 3 a.m., after a couple of gin tonics, we got out the logic analyzer and an iPhone 7, and we started looking at the signal. Now, Lightning is pretty simple. If you take a look into the Lightning connector after removing all the lint from your pocket, you can see 8 golden contacts. And these are all the contacts there are. And so while the connector has 16 pins, the plug only has 8 pins. That is, unless you have that one special iPad where they try to do USB 3 by extending the Lightning connector, but we don't talk about that one. So basically, we have 8 contacts, and Lightning is as proprietary as you can probably make a connector. So if you have a plug, a Lightning plug of a charging cable, and you decap it, you will actually find that there's a full microcontroller in the Lightning cable. And so if you connect a Lightning cable to your computer and you look at the signals on a logic analyzer, you will see that there's a lot of stuff going on. And so the first thing that you can see is that before any USB communication starts, there's this proprietary protocol going on that basically talks between the chip in the cable and the iPhone. And they do stuff like say, hey, I'm a cable. They send over the serial number of the cable and so on and so forth. And only relatively late, after sending a lot of data back and forth, does the actual USB communication start. And so you can see it takes quite a while to set all that stuff up, and then eventually we can see USB differential lines. This protocol that is used to talk to the iPhone is called SDQ or ID bus. It's a pretty simple one-wire protocol, and what happens in the iPhone is basically we use this SDQ or ID bus protocol to talk with a chip called TriStar. And TriStar is basically a multiplexer. And so internally to TriStar, there are connections to the internal serial bus, so to UART, to USB, to JTAG, and so on and so forth. And when we plug in a Lightning cable, the iPhone will ask the cable, hey, what do you want the Lightning pins to be? And then the cable will say, if you have a charging cable, please speak USB and serial, and so on. And this will basically change the state of a couple of pins on the connector to be USB, to be serial, and so on and so forth. Now, all of this is wonderfully documented for years, and so this was not new when we did it, and this was known since like 6 years or something. And it's a pretty simple protocol, and so we can pretty simply implement it ourselves. For example, on a Raspberry Pi Pico. And so we just take a Pico, we implement the protocol there, and then when we connect it to a phone, the phone asks who's there, and we just say, hey, I'm totally USB serial cable, and then we can do this. And all you need to build this is a Lightning extension cord from Amazon or so, connect it up to your Pico, and then after a couple of lines of C, we had a serial cable for the iPhone. We just invested 100 hours instead of spending $18 on AliExpress. Nice. But serial is relatively boring. What about JTAG? Now, JTAG is actually on the iPhone SWD, which stands for Serial Wire Debug. It's basically the JTAG interface by ARM that uses less wires. And the way JTAG is generally used is that you have a debug probe, which normally is a tiny device, and you have a target, which can be a microcontroller board under most circumstances, or a full-fledged iPhone. And we connect the debug probe to the target using 2 wires, a clock line and a data line. We call these SWCLK and SWDIO. We won't go into too much detail, but it's important to know that there are 2 signals that we need access to, basically. And using SWD, we can halt the CPU, we can single step, we can read memory, we can read registers, and so on, all that interesting stuff. And so we wanted to do that ourselves on the Pico without having to buy a Kanzi cable. And so easy enough, when the iPhone asks who's there, we just say, hey, please speak USB, UART, and JTAG to us. And then 2 of the pins in the Lightning connector will suddenly be JTAG. If you do this the messy way, it will look like this. And so if your desk is a mess and you have a debug probe separately connected to the Pico, to the iPhone, and a logic analyzer to see what's up. And after a couple of hours of debugging and a week of fuzzing the SWD stack to figure out a missing bit, we actually got JTAG on the iPhone. And so our probe connected, and we could do nothing, because unfortunately SWD can be locked. fully or partially. So basically, when you buy a device off the shelf, generally the SWD stack will be locked down because you don't want anyone to just, go to your phone, plug in a cable, and dump memory, right? Sounds like a bad idea. And so production iPhones and production devices in general tend to have this SWD or JTAG interface completely locked down. Luckily for us, the Checkbrain team found a vulnerability and built an exploit called Checkmate. And with Checkmate, which was a boot ROM exploit for the iPhone 7, I think, till X, we can actually first compromise the boot ROM, and then we can also demote the device. And demotion, basically, in the context of iPhones, means that we make the device debuggable again. And so if we do all of this, we can suddenly connect to the iPhone via OpenOCD, which is an open source JTAG tool, and we can start dumping memory and doing all the fancy stuff that you might want to do. As you can see, we see all the CPU cores, the memory APs, and so on and so forth. So we did all that, and we put that all into the Pico. So we put the full debug probe into the Pico. We put the SDQ bridge in there to actually talk the lightning signals and so on. And in the end, we were left with this small setup where you have a lightning extension and you can actually debug the iPhone 7 to X using this, or you can read memory and so on and so forth. This was apparently helpful to a couple of people, which was really nice. And now, obviously, this needs a name. Now, all these cables that you can buy are named after apes. And so you have the Kanzi Cable, the Kong Cable, the chimp or chimpanzee cable, the Bonobo Cable. But luckily for us, they didn't yet choose the best monkey, which is the Tamarin monkey, because it has this super impressive mustache. And so we called ours the Tamarin Cable. And this is all open source. You can find it on GitHub. We also did some hardware at some point, but chip shortage kind of got in the way. And so now we mainly, given that Lightning is on the way out, we are not producing any hardware or so. It's fully open source. It gives you a serial console, SWD probe. You can do reset DFU and so on. And it supports iPhone, iPad, Apple Watch now too, thanks to Teamstar. And it costs roughly $10 to build. Awesome work done. But then, something happened, which kind of got in the way of, making my work useful. And basically, with the iPhone 15.
So we're bringing USB-C to iPhone 15. It enables charging, transferring data, playing audio and video.
All that work for nothing, basically. So Tamarin is dead. And what's even worse, in this presentation, they didn't mention all the other interesting stuff you can hopefully do via USB-C, such as JTAG and serial. So now, if you look at the technical aspects of USB-C, USB-C has a lot of pins. And so given what we just saw was possible on Lightning iPhones, I was hopeful that maybe we can somehow map our SWD on some of these, right? We have enough pins, should be possible. And they still need to debug the iPhone somehow, and so hopefully for us, there are ways to do exactly that. Now, the iPhone 15 is not the first USB-C device by Apple, right? The MacBook has been USB-C for years, the iPad has been USB-C, and so on. But I never looked at any of those. I don't really have had a lot of interest, I would say, until the iPhone 15, mainly because after I published Tamarin, I got a lot of messages, well, what about USB-C, this, that, and so on. And it turns out that other people actually took a look at USB-C on these devices. And so, for example, the T8012 team actually analyzed the Type-C port controller that Apple uses in their MacBooks. And so on older Intel MacBooks, they actually dumped the firmware of this Type-C controller. This is a photo that was nicely shared by home user. And this still works on modern M1 MacBooks, right? Like you can still dump the firmware using a debug probe in system. And so this is pretty cool because it allows you to exactly analyze what's going on this Type-C controller. Versus on the TriStar, we never actually had a firmware to analyze what was actually possible. At least I hadn't. Now, what they found out is that basically USB-C uses something called configuration channels. And this configuration channel is basically used for USB power delivery negotiation. And so when you plug in a charger into your MacBook, the charger will send a message to the MacBook saying, hey, I can offer 5 volts, 9 volts, 20 volts, whatever. And then the MacBook will say, oh, yeah, give me 20 volts and 3 amps. And then the power supply will say, all right, and then turn on the power supply and mention to the device that it's ready. And all of this is done via these configuration channels. And that's not done like on USB 2 with like random resistor values and whatever, but instead we have a full protocol, a full bidirectional protocol going on there that basically uses Manchester encoding and so on and so forth. And one of the features, if you read the USB PD specification, is called VDM, which stands for Vendor Defined Messages. Basically, a vendor can take the USB-C power delivery communication and add custom commands to it. And the T8012 team found that Apple did exactly that. And so they called it Apple VDM, and they were able to reverse engineer the firmware and found out that, for example, there's an action hex 10 that when you send it to the iPhone, or sorry, to the MacBook at the time, will reply with a list of supported actions. And we can send those actions to the MacBook and to this chip and see what happens by just analyzing what's going on around the USB port. On MacBooks, the port on the left furthest away from you is the most powerful port because it contains a lot of additional debugging interfaces and so on. And on the inside, we basically have the MacBook, we have the Type-C controller in the MacBook, directly in front of the USB-C port, and we call that controller ACE. That's just a string that's in the firmware, and there are different versions of ACE. And so currently we know of ACE 1, ACE 2, and ACE 3. And ACE is basically the gateway from USB-C to the system on the chip in the iPhone. And so ACE does the USB or Thunderbolt negotiation. It also can provide a serial console and much more. And so this ACE chip can basically be used to map different functionality onto certain pins on the USB-C connector. So for example, if we send VDM action 306, we get serial on our USB-C port. So very, very similar to what we saw on Lightning iPhones, just a tad more on USB-C. But how can we actually send VDMs? So this is not something you can just do using libUSB or that you can just do from user space normally. But the awesome folks from Asahi Linux found out that they can write a tool called MacVDM tool that is based on another tool by Oli called Thunderbolt Patcher that allows them to send from a Mac to another Mac these VDM commands. And this MacVDM tool even supports serial, and so you can actually use your Mac as a serial console for another Mac. It supports rebooting the device, and it even supports putting it into DFU using these custom VDM commands. And so my hope was, if it works on the other devices and it works on the iPad and so on, maybe this works on the iPhone 15 too. And so I pre-ordered the iPhone 15, and on the day where I got back from holidays, the iPhone 15 finally arrived, and I could give this a try. And it turns out it's the same on the iPhone 15. We can use VDM to reconfigure the USB-C port to do interesting things, such as getting the serial boot output of the iPhone. Now, using MacVDM tool for me as a hardware hacker, not in general, has a couple of disadvantages. So first off, because it's Mac to Mac, it only supports serial, DFU, and reboot, basically. And I need an additional breakout to access the other USB-C pins to work with anyway. Also, enabling the serial console requires disabling system integrity protection and customizing the kernel. And so after I did that on the next upgrade, my kernel didn't boot anymore, and I had to do figure out how to restore that and so on, which is easy, but it's not particularly comfortable. Then I found out that somebody else felt the same way. And so Mark Zingier, aka Mats at kernel.org, designed the Central Scrutinizer, basically a piece of hardware that is a hardware serial adapter for these MacBooks. And so it does this whole USB power delivery negotiation and then turns the Mac into the mode where it speaks serial. And basically very similar to Tamarin, it also uses the Pico. And so it uses the FUSB 302 to speak power delivery and then enables level shifters to speak serial. Now, I was very hopeful that I could just use this board, modify it a bit, and be ready to debug the iPhone. But unfortunately, it didn't work. And so when I hooked it up, I can plug it in, and I can see some activity, but it didn't work. And so I started measuring. At that point in time, I wasn't particularly familiar with power delivery, and just fiddling around sounded better than reading a 600-page specification. And so I just started measuring, and I found out that basically the charging voltage, or the 5-volt rail of the USB-C plug, was dropping down when you plugged in the iPhone. And so I modified the Central Scrutinizer, added a small USB switch to provide power, did some very minor firmware modification, and suddenly it worked sometimes-ish. And so I could basically use the Central Scrutinizer, which gives me access to all the interesting pins, to reboot the iPhone, and I could even get serial on my logic analyzer, and so on and so on. But again, right, like now we just have serial, like Big Whoop, we just had serial, using MacVDM tool 2. But on the Asahi Linux wiki, there's a huge article about USB power delivery on the on the MacBooks. And they found a lot of different commands there. And so for example, they found actions that let you reboot the device. They found actions that let you, go into DFU, debug UART, debug USB. They even found some I2C buses that you can map to there. And at the very bottom of the page was this small sentence here: 0206, weak, good chance this is SWD. Exactly what we're looking for, right? And so I modified the Central Scrutinizer firmware to send that command over, connected my debug probe, and after debugging this for, again, a couple of hours, I got successful. I could connect with my debug probe, and we can see that it says found debug port with ID 4BA02477, which indicates that, yes, we are talking JTAG to the iPhone 15. Awesome, finally. Unfortunately, this found SWDP is the only good thing in the entire log, because the rest are errors. So we can't debug, obviously, because it's a production device, right? Like we didn't really expect this to work. I just wanted to see if it can be done. And so, well, we basically wasted a lot of time, right? So, or did we? It turns out that basically in the device there's a debug port, and we can connect to this debug port using SWD. And this debug port, in turn, gives us access to the other access ports in the device. And so there might be memory access ports, there might be internal memory buses, or JTAG APs, and so on and so forth. And while we can't do anything useful on the iPhone, we can still explore the APs. And so, for example, let's try to do a hardware demo on stage. Great idea. And so, for example, I have an iPhone here connected to some hardware, and we can see it says communication initialized. And so I'm going to go into JTAG mode. It says JTAG mode enabled. And now I can just use OpenOCD using the interface Xamarin and the target iPhone 15. And we can actually connect to this. And for example, I tested this demo before. And for example, read certain memory of the debug interface. This is not particularly useful. And we can even enumerate all the, we can even enumerate all the other access ports. And we can see that there are only 2 access ports available. One mem AP, which is basically just something of the debugging hardware, and then also an additional JTAG AP. This is not particularly useful, right? And so we got JTAG, but unfortunately it's completely useless on the iPhone 15. Somebody else told me that it actually works to debug on the MacBooks with T2, but that's not something that I'm particularly interested in. And so at this point I wasted a ton of time and a ton of hours to basically get essentially nowhere. However, in the documentation that I showed earlier, there were also other buses mentioned, right? And so if we look at the wiki, we can, for example, see that on MacBooks, there are 2 commands that map I2C buses onto the USB-C connector. And so let's explore the other buses. But for that, I needed slightly different hardware, because I didn't want to fiddle around with having a very rough setup every time. And so instead, I reached out to Marc Zunier and I asked, hey man, I did this Xamarin in the past. Do you mind if I do a Central Scrutinizer-ish device and call it Tamarind C and so on. And he was like, no, please go. And so I designed a board I call Tamarind C, which basically uses 4 bidirectional level shifters. And so we get access to all interesting pins that we can get through a USB-C cable. It has a USB power switch, and so while we do this, we can actually charge the iPhone, because on Macs, you have enough USB ports to also just plug in a power supply, but on the iPhone, we only have a single port. And it also has a full SWD probe integrated, as you just saw. Hardware and software will be fully open source later today. I even have some PCBs to give away. And basically, with Tamarind C, I'm now able to do the same as with MacVDM. I can, for example, reboot the device, and then it will enter the serial console, and we get the serial boot output of the iPhone 15. But we want to explore the other buses. And so it turns out that using VDMs, we can map 3 different functionalities onto the USB-C port. So we can map things onto the sideband use pins, which require a USB 3 cable. We can map them on the upper pair, which is never connected by a cable, and so we'd have to put a plug onto our device. And we can map stuff to the lower differential pair. And so we can map 3 different things at the same time. Time to investigate. And so basically, I hooked up a logic analyzer to all pins that we can map things to. I connected Tamarind to my computer. And then I started by looking at what actions are actually available on the iPhone. And so we saw this earlier, that TAD12 team reverse engineered a couple of the actions. And the iPhone is nice enough that there's actually functionality, there's actually functionality to get the supported actions. And so, for example, in Tamarind, using the firmware, you can just press F. And this will retrieve all the supported VDM actions. It will also tell you which ones we already know about, and which ones we may not know about yet, that we can investigate. And so based on that, I started the logic analyzer and started recording what's going on the device when it boots. And so we can see there's a bit of activity on the different buses that we have mapped. And a couple of these are fairly interesting. So the first one that we can look at is this one up here, which is some 6 megahertz baud rate UART, which I've never seen anywhere else. And then we also have this other weird signal here. And this signal is kind of interesting because it looks like I2C on the first look or SPI or so, but it actually isn't. And the first question when you see a protocol is, where does it come from? Which part of the device does it actually causes it to come? And I talked to Jiska and explained to her, hey, I have no idea where the signal comes from. Do you have an idea how I can figure it out? And she mentioned that on the iPhone, you have a tool called sysdiagnose. And with sysdiagnose, you can test all the hardware in the phone and will generate a log file that you can then analyze on your computer. And so I could potentially correlate that. And so I built a small app that shows the current kernel time, started the analysis, and sniffed the entire thing on the logic analyzer. And eventually, I could see some data traffic on the lines that I was interested in, and I could basically figure out the point in time where the interesting stuff happened. Now, funnily enough, this works best with a gaming monitor because you have a higher refresh rate, and so your timestamp gets much more precise. So if you need an excuse to buy a 144 Hertz monitor. And then I analyzed the log. This took a bit of time, and I eventually found that the activity happens every time that a tool called HPM Diagnose is started or terminated. And HPM Diagnose is also available on Apple Silicon Macs. And so there's a lot of similarity between the iPhones and the Macs. And so nicely enough, you actually get a man page on Mac that tells you, hey, this is a tool to help troubleshoot USB-C issues. And so I ran the same tool on my MacBook and sniffed the traffic at the same time. And it turns out that on the MacBook, there's this control channel that goes from the system on the chip to the ACE. And that one we basically can see and sniff using Tamarind on the MacBook Pro. But we just saw that this signal is not I2C. It has a clock line that's idle low, which is physically not possible for I2C. And also, it has a very weird amount of bits, like 13-bit transmissions and so on. It has this weird activity on the data line, which I don't understand, and so on and so forth. And after a lot of Googling random things, it turns out that this is actually SPMI, or the System Power Management Interface. I've never seen this in my life before. And luckily, there's a very extensive Wikipedia article that explains all the details about this. It's exactly 3 sentences long. And only tells you that SPMI is specified by the MIPI Alliance, and that's basically it. And so then you try to visit the MIPI Alliance and are greeted by this error message. Insert coin to continue. So to get access to this standard, I would have to become a MIPI adopter or contributor. Luckily / unfortunately, I earn less than 250 million a year, so it would just have been $4,000 annually. And so things you totally should not search is file type PDF, MIPI confidential SPMI. And which unfortunately, in my case, totally did not give me the first version of the specification, which didn't outline all commands. But then I found this 58-minute video on YouTube in which someone happened to open the command sequence for MIPI 2.0, which we now fully have. And so I could start analyzing this, could take a look, and could actually build what I believe to be the first open source logic analyzer plugin for SPMI. And so you will be able to find this on GitHub later today. And it turns out that the communication we are seeing is the communication with the ACE3 in the iPhone. So in my MacBook, I have an ACE2, which apparently speaks I2C. And in the iPhone, we have an ACE3, which is this SN201 chip. So it looks like basically the system on chip talks to the ACE3 using SPMI. Maybe. I don't know, because there are a couple of more interesting things in the logic trace. And so, for example, if you look at the registers of the device, it actually claims to be speaking I2C. And so maybe there's some weird SPMI to I2C bridge going on. I don't know. But yeah. So I decided that not everyone has a logic analyzer, and so I actually implemented SPMI sniffer support on Tamarin C, including an ACE3 decoder. And so you're now able to analyze the ACE traffic on your iPhone externally. I also tested a basic transceiver, but I can't get it to respond via USB-C. It only works in system, and I will publish this once I get it fully working. So now we looked at a lot of buses, and we figured out we can communicate with some of them, and so on and so forth. And so was there anything interesting beyond just looking at the port? Well, it turns out that on one device that I will not mention today, I was actually able to find and also kind of exploit a vulnerability using Tamarin C by speaking to one of the buses, is what I would say. I will also say it's not the iPhone 15. And I also found one potential low to mid severity vulnerability in some of the other USB-C devices that are more interesting, let's say. So hopefully, after 90 days are up, which I think 85 are remaining because I had to disclose on Christmas, we will have something interesting. But still, I got some stuff for you today. So releases, the hardware and firmware for Tamarin C will be released, SPMI analyzer will be released, the sniffer and the I2C transceiver will be released. And so now you can actually experiment with USB-C on the iPhone, on the MacBooks, in a simpler fashion. It's not perfect, it's hacker firmware, it's not super stable, but it should work. And I had a bug issue in my first revision, and so on the 21st of December, I had to order new PCBs. And so Isla was nice enough to super rush these so they get to me before Christmas. And they were nice enough to also give me 100 PCBs to give away today. And so if you're interested in this, feel free. I have 100 PCBs with me. And I also have some parts. So if you plan to hack something on site, let me know, and maybe I can give you a couple of parts to set this up. Now, before we stop, there's also, if you ever want to dump ACE, you can actually use Tamarin now to dump the ACE in system. So if you have good motor skills and are good at soldering, Tamarin can be used for that. Now, finally, before we go, so there's also something called Kanzi in system. And so some people think that in the future, USB-C will not be used for debugging anymore, but instead, there's a debugging probe already integrated into the iPhone. You can enter that mode using VDM, and there's some work out there. I've not really looked at it, but I want to encourage you all to maybe take a look and have a look at Kanzi in system. One last fun fact, the iPhone 15 is actually not the first iPhone that speaks USB-C. And so it turns out that when you connect a USB-C to Lightning cable to your iPhone, then the Lightning cable will actually tell the Lightning cable to please speak USB-C. And then it will actually map USB-C power delivery onto the Lightning connector. And so you can do USB-C over Lightning while you're USB-C. So, I mean, all right. And with that, that's all I have for you today. So thank you so much for coming. And yeah.